Welcome to this explainer. Okay, grab your magnifying glasses because today I'm putting on my astrophysicist hat to take you on a literal cosmic detective story. For the longest time, right, our understanding of space was entirely dependent on what we could actually see. Visible light captured by telescopes. But the universe, it's full of this incredible invisible architecture. And today, we're tracking down invisible phenomena that are completely reshaping our understanding of space, time, and basically reality itself. Let's get into it. So, how do you map a universe you can't even see? It sounds like an impossible riddle, right? But our clues in this modern cosmic investigation, they aren't made of visible light. Instead, we're looking for invisible ripples stretching the very fabric of space, and these inexplicable split-second subatomic strikes hitting our atmosphere. Honestly, these are the true fingerprints of the universe's absolute most extreme unseen events. To really understand where we are right now, we have to look at the sheer escalation of these clues over the last century. Going way back to 1916, Albert Einstein first predicted that space isn't just some empty void. It's actually a fabric that can be stretched and squeezed by gravitational waves. Now, it took decades to prove him right, but then things really started speeding up. In 1991, we detected an incredibly powerful microscopic anomaly that researchers literally called the "oh my god" particle. Fast forward to 2015, and the LIGO Observatory finally caught the very first direct detection of a gravitational wave from colliding black holes. Then, the plot thickens even more in 2021, when another mysterious subatomic bullet, the Amaterasu particle, struck Earth. And just recently, in 2023, the Nanograv collaboration detected a continuous background hum of gravitational waves. This whole timeline reveals a universe that is just constantly, relentlessly being stretched, squeezed, and pierced by forces we can't even see. Section 1. Tracking the cosmic hum, listening to the universe's deepest rumble. Let's start with our first major suspect. We're looking at a continuous, extremely low-frequency hum that's rhythmically stretching and compressing the spacetime of our Milky Way. But, how do you actually hear a hum made of gravity? Well, scientists came up with this genuinely amazing method called a pulsar timing array. Instead of just building another telescope down here on Earth, an international collaboration of astronomers used the galaxy itself as a detector. No, really. They used 67 highly precise, rapidly rotating dead neutron stars. These are called millisecond pulsars, scattered all across deep space. Think of them like cosmic lighthouses. These pulsars shoot beams of radio waves right past Earth hundreds of times a second, and they do it with the stunning precision of an atomic clock. So this gives us an actual step-by-step procedural guide for tracking the invisible. Step 1. Scientists continually monitor the precise radio flashes of these dead stars. Step 2. They track incredibly tiny arrival delays. And we're talking about fractions of a single microsecond here. Why? Because as a low-frequency gravitational wave sweeps through our galaxy, it actually alters the physical distance between Earth and those pulsars, which slightly delays the flash. Then, step 3, they mathematically correlate these pairs using a specific curve called Helling's downs. This is absolutely the crucial step. It allows them to filter out all the local signal noise and successfully isolate the actual, real cosmic gravitational wave background. As astrophysicist Luke Zoltan Kelly perfectly puts it, it's only the statistically coherent variations that really are the hallmark of gravitational waves. You see, you get little variations on millisecond scales all the time just from standard cosmic noise. The real game changer came from correlating those tiny changes across 2,211 distinct pulsar pairs. Bringing it together, that massive international collaboration is exactly what finally confirmed that the signal wasn't just local static, but a true universe-spanning rumble.
Moving to Section 2. Ripples from dancing giants, the source of the hum.
So, what could possibly be massive enough to vibrate the entire cosmos? We have to address the giant cosmic elephant in the room here. Our prime suspects are supermassive black hole binaries. Imagine hundreds of thousands of pairs of supermassive black holes, each weighing billions of times the mass of our sun, orbiting together at the centers of merging galaxies. Think of these black holes like incredibly heavy waltzing dancers on a wooden dance floor. As they spin around each other, their massive orbital dance rhythmically vibrates the local space-time curvature. These overlapping ripples from across the entire 13.8 billion year history of the universe, they combine to create that exact background hum we're detecting today. And we're talking about totally mind-bending scales here. The amplitude of the signal detected by Nanograv suggests these binaries skew toward incredibly high masses. Actually, scratch that. unimaginably high masses. While we used to think supermassive black holes maxed out around maybe 20 billion solar masses, the sheer power of this data suggests some of the pairs creating this hum could be up to 40 or even 60 billion times the mass of our sun. What's really cool is this discovery actually helps solve a 50-year-old astrophysics mystery known as the last parsec problem. For decades, theorists wondered, okay, when two galaxies merge, their central black holes orbit each other, but do they eventually just stall out a few light years apart, or do they inevitably merge? Well, the mathematical evidence linking this observed background hum to these binaries suggests that they absolutely do not stall. They successfully navigate this bottleneck, coalescing and emitting the very gravitational waves we're listening to right now. All right, Section 3, the lone wander particle, a strike from the void. Now let's pivot dramatically from a massive, slow, galaxy-wide background hum to our second suspect, a sudden, completely inexplicable microstrike. In 2021, the telescope array in Utah detected a single, extraordinarily high-energy particle striking our atmosphere. They named it the Amaterasu particle, after the Japanese sun goddess. And the energy reading? A mind-boggling 244 exa-electron volts. To put that completely astronomical number into perspective, when this microscopic particle collided with a nitrogen nucleus in our atmosphere, the collision was roughly 200 times more energetic than the highest collision energies ever achieved by humanity's Large Hadron Collider. And this brilliantly illustrates just how crazy that is. A single, invisible, subatomic particle moving at effectively the speed of light packed the exact same kinetic energy as a standard household brick being dropped to the ground from your waist. Just imagine that for a second. A microscopic speck hitting with the concentrated force of heavy building material. It's wild. But here is where our detective story gets wonderfully weird. Where did it come from? When scientists traced its trajectory back through the cosmos, the origin point was, well, nowhere. It seemingly emerged from the local void, an empty, desolate expanse on the absolute fringes of the Milky Way. There are no supermassive black holes there, no violent supernovas, literally no known high-energy environments capable of acting as a cosmic particle accelerator. It was quite literally a shot in the dark from the dark.
Section 4. Macro hum versus microstrike, two extremes of the cosmos.
As an astrophysicist, it is incredibly exciting to bring these two bizarre clues together and compare them side by side. Just look at the stark contrast here. On one hand, we're tracking the gravitational wave background, phenomena on the scale of billions of solar masses, producing this continuous, persistent hum that ripples through the fabric of space, originating from the most massive dancing giants in the universe. On the other hand, we have the Amaterasu particle, a subatomic speck producing a split-second, highly violent transient strike, originating from an empty void. They are two absolute extremes of the cosmos, yet both are completely invisible to the naked eye. So the crucial point is captured perfectly by researcher Toshihiro Fujii. He notes that these mysteries are, quote, suggesting possibilities of unknowing astronomical phenomena and novel physical origins beyond the standard model. Both the massive, slow hum and the violent microstrike are essentially telling us that our current scientific models are incomplete. They point to the thrilling potential for discovering entirely new physics. And this matters so much because it means the universe still has fundamental secrets about reality left to teach us.
Section 5. Future telescopes and unknowns, the next chapter of discovery. So how do we solve these mysteries? Well, the next chapter of this detective story relies heavily on upgrading our investigative tools. We have some absolutely incredible upcoming telescope projects that will map the invisible structure of deep space. The Roman Space Telescope, Euclid, and the Vera C. Rubin Observatory will utilize spatial visualizations and techniques like weak lensing to observe exactly how gravity subtly bends light, which helps us trace the universe's cosmic web of matter. Meanwhile, LISA, a proposed space-based observatory, will literally take our gravitational wave detection into orbit. That's going to allow us to detect merging binaries thousands of years before they actually collide. And, with better data comes better statistical tools. For instance, future observations might actually solve the mystery of that empty void. Using advanced models, researchers are exploring whether the Amaterasu particle didn't actually originate in the void at all, but was simply deflected by the cosmos. It's highly possible its path was severely bent by cosmic magnetic fields originating from a nearby violent starburst galaxy like Messier 82. We just need the next-gen instruments to go out there and prove it. And of course, we can't forget the ultimate invisible suspect influencing all of this: dark matter.
This invisible mass warps the very fabric of space and could totally be interacting with these signals. Scientists are constantly hunting for subatomic dark matter suspects like WIMPs. Those are heavy, slow-moving hypothetical particles. Or axions, really low-mass particles that might actually solve matter-antimatter imbalances. Or even primordial black holes, these ancient atom-sized black holes left over right from the Big Bang. Any one of these could be the missing puzzle piece in our cosmic map. Which brings us to the ultimate question. We've mapped out gravitational rumbles from dancing supermassive black holes, and we've tracked invisible, high-energy bullets flying seemingly out of nowhere. If our universe is essentially a massive, dark room filled with waltzing giants and invisible bullets, what else is hiding out there in the void, just waiting to be found? Keep looking up, stay curious, and I will see you in the next explainer.